and how is the particle B moving. So for that, you imagine a rod. They are all allowed to move in a random direction. The only constraint is that in this question, first of all, I will use a mathematical thing. All right, question number 24, 25. It's a good question. It's an easy question actually. AB section is straight. BC section is again parabolic. It looks so. In question number 21, it says that a particle moves with a constant speed of 2 meters per second on a circular path of radius 4 meter. Particle B moves on a straight line coinciding with the diameter of the circle but maintaining a constant distance 4 meter from particle A. So guys, when you think about the situation given, at first it might appear as if it's an impossible situation. Yeah, but that would be your first thought only. If you give a careful consideration to it, it would turn out that the particle A is moving on a circle. And how is the particle B moving? So for that, you imagine a rod or a tunnel-like situation. You imagine a tunnel which coincides with one of the diameter of the circle. Okay, so the situation is somewhat like this. Like if the particle A is here at any moment, this is radius R, which is given to be 4 meter. Okay, and particle B stays at the same distance, that is 4 meter, that is equal to the radius of the circle. So particle B would be here somewhere. Particle B would be here somewhere. So you imagine AB as a rod, and you can also imagine OA as a rod. So the situation is that OA is a rod, AB is a rod. These two rods are jointed at A. They are pin jointed at A. B is constrained to move in this tunnel, which we are representing with the green color. Okay, and O is fixed point. So as this rod OA rotates like this, B moves forward. So this is the situation right now. Okay, now how do we solve this situation? Like, of course, A will have a velocity in the tangential direction, and also keep in mind that this tangential direction is not along AB. In the figure that I've drawn right now, it may appear as if the velocity of A, that is V. Let's give it a name V. Let's call this as V. Okay, so the velocity of A in this figure right now, it may appear to you, or you may get confused. You may assume that I've assumed V along AB, but that's not the case. V will be along the tangent, and AB will be in a different direction, except for some specific instant. Okay, so let's draw a figure that represents the general situation and let's try to find the relationship between V and VB. Once that relationship is there, I think we'll be able to solve most of the question. Like that we'll be able to address all the options. Okay, so let me draw a larger figure here. So let me draw a larger figure. I'll try to keep the color same. So I drew the circle in red color. Let it be in red color. I drew the tunnel in green color. Let that be in green color. Okay, at some instant, let's say A was here. Let's say B was here. So this is B, this is A, this is O. Now OA length is same as AB length. So at any instant of time, OAB, okay, OAB will constitute an isosceles triangle. They will constitute an isosceles triangle, which basically means that if this length is L, then the theta. If this angle is theta, then this angle will also be theta. Okay. Now the velocity of A would be along the tangent. Okay, that means it will be perpendicular to this. Now let me draw a horizontal line from here. Okay, so this angle also becomes theta, this angle also becomes theta. And if I extend the line AB, AB line is making an angle theta with the tunnel. Tunnel is horizontal, this blue line is horizontal, so this angle will also be theta. So the angle between the velocity vector of A and the line AB would be this angle. Okay, and how much would that be? How much would that be? So that would be this entire angle is 90 degree, then 90 minus theta. So this particular angle would be 90 minus 2 theta. Okay, this particular angle would be 90 minus 2 theta. So we will use the rod constraint, that is A and B are the ends of a rod. All right. So we can say that velocity of A, VA, along the rod, that would be cos of 90 minus 2 theta. This should be same as the velocity of B along the rod. So we will equate it with VB cos theta. So this will become sine 2 theta. So VA into sine 2 theta. Sine 2 theta can be written as 2 sine theta cos theta. This will be equal to VB cos theta. We can cancel out cos theta. So the value of VB comes out to be 2VA sine theta, and VA is given to be 2 meter per second. So it will become 4 sine theta into meter per second. So that is one thing we are going to make use of it. Another thing that you can take note of it, that when A was here, B would be at a distance of 4 meters from here. So B would be here. By the time A reaches somewhere here, B reaches here, and by the time reaches A here, like when theta becomes 90 degree, B would be here. And when A comes this side, B starts going this side. Okay, so B is here now. And when A comes here, B comes here. So in half a revolution of A, B goes from this point to this point, and this is again 4 meter. This is 4 meters. So 4 plus 4 plus 4 plus 4 is 16 meter. So B travels the distance of 16 meter in half a revolution. By the time A comes back to its original position, to its starting position, B would have traveled another 16 meter. B would have come back on its covered path. So B would have covered a 32 meter distance. Let's check out the options. So maximum speed of B is 4 meter per second. Yeah, that seems correct because the value of sine theta can take a maxima of 1 and that would happen when theta is equals to 90 degree. So yes, the option A is correct. Maximum speed of V. Now maximum acceleration of V is 2 meter per second square. All right. Now velocity of V is it is not changing direction. It is only changing the magnitude. So we can write that the acceleration of V will be equal to the rate at which the speed of V changes, and that will be given by 4 into cos theta into d theta by dt. And d theta by dt can be written as, how do you write d theta by dt? So here d theta by dt will become the angular velocity of OA rod. So that would be given by velocity of A divided by the radius. Now velocity of A was given to me 2 meter per second, radius was given to me 4. So R, I can cancel it out. So 2 cos theta meter per second square, that is the acceleration of V. And again, we can see that the acceleration of V attains a maxima of 2 meter per second square. So maximum acceleration of V is 2 meter per second square. Yes, even that is correct. During one revolution of A, distance traveled by V is 32 meters. Yes, we already figured that out. That is correct. Modulus of velocity of particle A related to the other is constant. Okay, let's check this out now. So if I want to write velocity of B, let's consider this as x direction, let's consider this as y direction. Let me change the color so that you can find out what I'm writing. Let me use white color. So velocity of B is in this direction. Velocity of B is in this direction. So VB will be equal to, or VB vector will be equal to, it would be 4 sine theta with a minus I cap. That would be VB vector. What about VA vector? So VA vector is making an angle of it's making an angle of 90 minus theta with the x-axis, with the negative x-axis. So let me do it on the next page. So VA vector is like this, and it is making an angle of 90 minus theta with the x-axis, or you can say theta with the y-axis. So when we are trying to write VA vector, it would be V cos theta j cap, and cos of 90 minus theta will become sine theta. So V sine theta minus I cap, and the value of V is 2. So it will become 2 cos theta j cap minus 2 sine theta I cap. Now, when you do VA minus VB or VB minus VA, let's do a VA minus VB. So VA vector was minus 2 sine theta I cap plus 2 cos theta j cap. This was VA vector. What about VB vector? VB vector was minus 4 sine theta I cap. Okay. So this becomes what? This becomes 2 sine theta I cap plus 2 cos theta j cap. And when we take the modulus of this velocity, we end up getting 2 meter per second, which is a constant value. So let's go back to option D. Modulus of velocity of a particle relative to the other is constant. So yes, even this option is correct. So for this question, all the 4 options are correct. A, B, C, and D, all 4 are correct, as we can see here. All right. Now, question number 22, it's a very interesting question, guys. If we try to solve this question by objective approach, this question is less than a minute question. Okay, it can be solved in less than a minute. But if we take out the options and we try to solve this question, we try to prove whatever is the solution to this question, whatever is the answer to this question. If we try to prove that, then it's going to take some kind of thinking and some kind of good logic from you. So let me first solve this question with the objective approach. So the question says that A, B, and C are crawling on a large horizontal tabletop, always occupying the vertices of an equilateral triangle, the size of which may vary with time. If I have instant speed of A and B are, so basically what the question says is that we have a tabletop and there are 3 particles. Let's replace ants by particles. So there are 3 particles which are allowed to move in any random direction. Okay, so this is A, this is B, and this is C. They are all allowed to move in a random direction. The only constraint is that they will maintain the shape of an equilateral triangle. All right, so the shape of the triangle can change, like not the shape, the side of the triangle can shape, the sides can increase in length, the sides can decrease in length, even the orientation can change. So the best way to imagine what is going on is, let's say you are looking at from the top. So what you see is a triangle. What you see is a triangle which is free to rotate and which is which can expand or contract, and the center can move it. So this encompasses all kinds of motion that you can imagine. So imagine a triangle which is rotating, which is shifting, okay, and which is changing its side length. So basically A, B, C, they are free. So this is the general scenario. Okay, now we have to choose the correct option. So whatever options are listed here, if they are generally true, so they should be true for any situation that I chose. All right, so let's choose a situation in which we are saying that let's make an equilateral triangle using 3 rigid rods. Okay, let this be A, let this be B, let this be C, and let's keep A as stationary and let's rotate this triangle with an angular velocity omega. Okay, so we are using 3 rigid rods of length L. Okay, you can see that the situation that I'm taking here is a subset of the situation that we are allowed to take. Whatever liberty has been given to us regarding the motion of the ant. Again, I can take this as one of the cases. So in this case, VA is 0, VB is same as VC, which will be equal to omega into L. You can see this. Okay, so let's try to check the option with these. Check these options. So what I'm trying to use here is elimination. Then I will tell you how you can prove this. Okay, so A option says that VC is less than half of VA plus VB. So VA is 0, VB is omega L. Let's give a name to omega L. Let's give a name to omega L. Let's give it as name as V. Okay, so 0 plus V. Okay, so VC should be less than VC should be less than half of V, which is not true. VC is equal to V. It is not half of V. Okay, so when I take this example, I find that option A is not true for this particular situation. So, which basically means that option A cannot be generally true. Okay, now the difference between option A and option B is only the equality sign. Again, by the same example, we can rule this out. Okay, here, C option says that VC should be less than VA plus VB. Here we can see that VC is not less than VA plus VB. Again, in this example itself, it is actually equal to the sum of VA plus VB. So we have ruled this also out, and B option is satisfied. We can see that VC is equal to the sum of VA plus VB for this particular example. So we have eliminated three options. The fourth option could not be eliminated. It is satisfying the example that we have taken. So obviously this must be the answer. So as far as finding the answer to this question is concerned, we have done that. All right, we've done that. Now let's try to prove this. So that was the objective approach. If you get this question in the exam, you can solve this question in the exam by the objective approach. But how do you prove it? Let's try to do that. Okay, so guys, coming back to what I asked you to imagine here, you can imagine the triangle to be rotating. You can imagine the centroid to be moving in any particular direction. The centroid can move with a velocity which is varying in magnitude as well as in direction. The side of the triangle is changing. The triangle is rotating. All kind of motion you can imagine. But let's go into the frame of A. Okay, let's go into the frame of A and then analyze the situation. So from this frame, A appears to be at rest, and again, B and C. Okay, B and C, they are allowed to move in any direction. Okay, keep in mind that now I'm not saying that we are dealing with a triangle made of rigid rods. All right, which basically means that at this very moment, the sides of this triangle may be changing at some rate. Okay, so velocity of B may be having a component in this direction, it may be having a component in this direction, which basically means that the velocity of B may be having maybe in any random direction like this, maybe. What I'm trying to, but so this is one of the things, velocity of B with respect to A, that is. Now, correspondingly, the velocity of C. Keep in mind that in this frame, A will always be at rest. We are sitting in the frame of A will always be at rest to continue for these particles to constitute a triangle. Okay, what should happen is that whatever is the velocity of B as seen by A, whatever this vector is making with AB line, the same should happen with VCA. All right, the same should happen with VCA. That means the velocity of C with respect to A has to make the same angle with line AC. It has to do that. All right, because if it is not doing that, then the shape will not remain triangular. You again, why am I saying this? See, in the frame of A, ultimately what you will witness is a rotating triangle, or the two rods, AC rod and AB rod. They are rotating and they are changing the length. All right, they are changing the length so that their length always remains equal. So that can happen only when this condition is satisfied. That VCA should make the same angle with AC as VBA is making with AB, and not only that, VCA should have the same magnitude as VBA. Let that magnitude be V for now. All right. Now, what this tells us is that if I draw a line along VCA, if I draw a line along VBA, this angle should be 60 degree, because this angle is phi, this angle is phi. So the angle that VCA makes with AC, the angle that VBA makes with AB, they are same, and the angle between AC and AB is 60 degree. So the same angle should appear here also. So we are using this piece of geometry. All right. Uh, so the situation right now is that we have figured out that VCA vector, okay, VCA vector and VBA vector, they will be equal in length. They will be equal in length, and they will have an angle of 60 degree in between. Okay. Now we are trying to think about VC. Remember the question, the options are talking about VC. We want to find out what values VC can take. So VC vector will be given by VCA plus VA vector. All right. In the ground frame, this figure was drawn from the frame of A. In the ground frame, VC vector will be given by VCA plus VA. So I'm asking you to add VA vector to both these red vectors, and adding VA vector to both these red vectors will respectively give you the VC vector and the VB vector. All right. Okay. So we are going to add VA vector. Now what I'm going to do, I'm free to choose any magnitude of VA vector. I'm free to choose any direction of VA vector. So I prefer to choose a direction of VA vector that can give me a maximum value of VC vector. All right. So I have this vector with me. Here it is. I want to add a vector to this vector so that this vector can have a maximum magnitude. What will you do in this case, guys? Are you thinking about adding VA vector, like choosing VA vector such that VA vector is in the same direction as VCA vector? Because in this way, like when you are supposed to add two vectors so that you can get the maximum magnitude of the resultant, then you try to keep those two vectors in the same line. All right. So in this particular case, I have done the same thing. So this entire length indicates VC, and not only this, this is the maximum value of VC that we can get. This is the VC max. Okay, so this is the maximum value of VC that we can get. And how much is that? So if I am representing magnitude of VCA and magnitude of VBA with V vector, okay, then this length is V, this length is V. So in this particular example, the magnitude of VC, which also happens to be the maximum value that VC can take, is V plus VA. So let me write it as equation A. All right, so that is the case. Now, what about VB vector? What about VB vector? So the resultant of VA and VBA, remember, V vector can be written as VBA vector plus VA vector. So this would be the resultant. This would be the resultant. Okay, so this is the VB vector. Now, VB vector is the resultant of VA and VBA, and the angle between this vector and this vector is 60 degree. All right, so if I have to write down the magnitude of VB, it would be root of VA square plus V square plus 2VAV and cos of angle between them, which is 60. So it becomes root of VA square plus V square plus 2VAV. All right, so let me write it again here. So VB is root of V square plus VA square plus VAV. All right. Now, can I say that this entire thing is certainly greater than V square? Like, can I say that this is greater than root of V square? Because we are adding something to V square and then we are taking the root. So obviously that is going to be greater than V, the square root of V square, which basically means it is greater than V. So if VB is greater than V, then it means that VB, or maybe it can be equal. All right, I can put an equality also here. When will the equality be satisfied? The equality can be satisfied if VA is taken to be zero. All right, if VA is taken to be zero, then the equality will also satisfy. All right, so VB can be greater than or equal to V. So VB plus VA. Okay. VB plus VA. VB plus VA can be greater than or equal to V plus VA. And what is V plus VA? This is the maximum value that C could have taken. So VB plus VA, VB plus VA can be greater than or equal to the maximum value of V. And the maximum value of V will always be less than or equal to any other value of VC. So hence we have proven that VB plus VA can be greater than or equal to VC. So this is the proof, guys. So this is the proof. Again, it's a logical, a thoughtful proof. The mathematics is less here. The vector calculations are there, so you might find it a bit difficult to understand. But yeah, as far as the objective approach goes, we can solve this question in seconds by using the objective approach. As far as the proof goes, here is the proof. I've given it to you. I hope you enjoyed the proof. The answer would be option D. All right. Thank you, students. Now, this question, okay, this is a good question, guys. In this question, first of all, I will use a mathematical thing. All right, I'm like we are going to find one particular expression repeatedly. So, and we would be interested in knowing how that expression changes with time. For example, let me write a function of time as t divided by root of alpha plus beta t square. I want to know how this function changes with time. That is, I want to know derivative of this function. So that would be root of alpha plus beta. What I'm doing here is I'm first giving you the math that we are going to use in this equation so that once we are delving into the physics, we are not actually going again and again too much into the math. We will directly use the result that we are getting here. All right. So f dash t would be this into 1. All right. Then minus t and then half root of alpha plus beta t square into beta into 2t divided by alpha plus beta t square, and it comes out to be this 2 gets cancelled, so it becomes alpha plus beta t square minus beta t square divided by alpha plus beta t square raised to power 3 by 2. Now if alpha is a positive number, then we can say that f dash t would be positive, and if alpha is a negative number, then f dash t would be negative. So basically, if alpha is a positive number, then f would be an increasing function of time, and if alpha is a negative number, then f would be a decreasing function of time. Now, with that knowledge, let's begin. Now, the situation says that there was a very tall tower or a cliff. Maybe let's go back and see. Projectile reflected from the top of a tower. Okay, all right. So we have projected a projectile from here, and we have thrown it horizontally. Well, let's say with some speed u. The question says that horizontally. All right. The question says that we have projected horizontally. Assume acceleration due to gravity to be uniform in the origin of the coordinate system. So this is the origin of the coordinate system. So let me choose the coordinate system like this. Let this be x-axis. Let the downward direction be y-axis. So the projectile will start traveling somewhat like this, all right? And at some point, at some general instant, this would be like if the projectile is here, this would be the position vector, which is also equal to the displacement vector, and this would be the velocity vector, and the acceleration vector would be vertically downwards. So if I have to write the position vector, I will write it as UT I cap plus half GT square into J cap. Note this. Remember that I've assumed y direction in the downward direction, like positive I is the downward direction, and therefore we are writing like this. What about the velocity vector? The velocity vector would be written as UI cap plus GT J cap. What about the acceleration vector? The acceleration vector would be written as G J cap. So we have written R, B, and A in terms of IJ and time as the functions of time. Now let's go back and see. It says that the components along and perpendicular to position vector are known as radial and transverse component respectively. So what are we talking about? Component along, let me see, along the position vector. So right now this R vector is the position vector. So a component in this direction. So this is radial. Okay, component in this direction, they are called the transverse. Okay, so in this question, the radial direction is defined, the transverse direction is defined, and now we have to think about the radial component of the velocity. So guys, the radial component of the velocity means component of velocity. Let me write it here. The radial component of the velocity would be a component of velocity along r vector. And how do we write component of one vector along the other vector? We take the dot product and we divide with the magnitude of r vector. So that will give us component of velocity vector along r vector. All right, let's do that. So VR will be V vector dot R vector. So this is V, this is R. The dot product will give us U square T plus G square T cube by 2. G square T cube by 2. And then we divide it with the magnitude of R vector. So magnitude of R vector would be, let me take T as the common thing out, and then we will have U square plus GT square by 4. So G square T square by 4 and root of this. One T gets cancelled, so we end up getting U square plus G square T square by 2 upon root of U square plus G square T square by 4. All right, now we have to decide whether this VR is it's increasing with time or decreasing with time, or increasing then decreasing, and things like that. This is what we have to decide. So let me write VR in a simpler form. Like what I see here is that some constant, even the constant is U square here, plus some constant into T square divided by root of C1 again. And then this is C2 by 2 T square. So we have to find out how this changes with time. So for that, let's check out the first derivative. So dVR by dt. All right. So this will be what? This will be root of C1 plus C2 T square by 2, and then derivative of the numerator, which would be 2C2T. Okay, minus, we will write the numerator. Okay, we will write the numerator, and then we will differentiate the denominator. So that is 2 root of C1 plus C2 T square by 2 multiplied by C2 by 2 into 2T. All right, and entire all of this divided by C1 plus C2 by 2 T square. So check this out. Now let's do the calculation on the next page, or let's see whatever we can do in this page. I can cancel this 2, and I will take this here. Okay, so let me write it here. So dVR by dt will be equal to root of I think denominator. Okay, this should be like this. Okay, this should be like this, and now this comes here. So guys, you can do this math yourself also, because you will understand better that way. If you try to do this yourself, you will have better chances of understanding. So this 2 and 2 will become 4C2. Okay, so 4C2 multiplied with C1 plus C2 T square by 2. All right. So I've multiplied this entire thing with this entire thing. Okay, and then we will have minus of C2T into C1T C1 plus C2 T square. So this is our numerator. This is our numerator. And what is the denominator? Denominator would be 2 times of this. So C1 plus C2 by 2 T square raised to power 3 by 2. So that is our denominator. So let's take the value of the numerator. So it becomes 4 C1 C2, and then plus 2 C2 square T square. Yep, that's correct. Minus C2 C1 T and minus C2 square T2 T cube. Are we getting a cube here? We are not getting a cube here, which tells me some dimensionally something is incorrect. So here was a T also. Here was a t also. So again, a t will be here and this will be q. Okay, now divided by whatever the denominator is. Because the denominator will be a positive number, I'm not interested in that. So this becomes 3c1 c2 t plus c2 square t cube upon whatever. And c1, c2, they are positive numbers. So this is definitely greater than zero. So we can say that VR increases with time. VR increases with passage of time. So we are sure about VR now. All right. So the radial component of velocity, it always increases. P option. Transverse component of the velocity. Now, how do we get the transverse component of the velocity? So you can get the transverse component of the velocity by using the fact that v square minus vr square should give you this. So how much is v square? Let's go back here. V square is magnitude of this, so that would be u square plus g square t square. So this is v, okay, square of this minus component, radial component. How much was radial component? Here it is. Here it is. So it would be u square plus g square t square by 2 square of this divided by u square plus g square t square by 4. There was a root. I have done the square and the square root of this entire thing. This is our transverse component of the velocity. Yep. Let me just check. I've copied everything correctly or not. Yes. Okay. So we'll do the calculation now. It's a mathematical question. You will have to do the calculation, guys. I know that most of us don't like to do all this calculation when we are solving physics, but we are forced with to do that right now. So I've taken this side and then u square plus g square t square by 2 whole square. Okay, and then divided by u square plus g square t square by 4. So let's do the math now. So this will become u raised to power 4 plus u square g square t square by 4, okay, plus u square g square t square by 4, that's okay, then plus u square g square t square, and then plus g raised to power 4 t raised to power 4 by 4 plus g raised to power 4 t raised to power 4 by 4, and then you have to subtract from this, the square of this, so the square would be u raised to power 4 plus g raised to power 4 t raised to power 4 by 4 uh, plus u square g square t square. All right. And this entire thing divided by u square plus g square t square by 4. And this entire thing is in root. Okay. Now let's see what all gets cancelled. So this u raised to power 4 gets cancelled. U square g square t square gets cancelled. G raised to power 4 t raised to power 4 by 4. This gets cancelled. So out of the what seven terms we had, uh, six terms are gone. So we are getting UGT by 2 divided by root of U square plus G square by 4T square. Notice that it has this form, like you take out UG divided by 2. You take it out as constant, so it is T divided by root of some alpha plus beta T square kind of form. It has where alpha is this and beta is all this. And we've already checked it out that this is an increasing function. So we can say that transverse component of the velocity also increases. Here we checked it, right? Here we checked it that this is an increasing function, so we are using it now. Now, radial component of the acceleration. Now, this is important, guys. Since we have already calculated dvr by dt, you may be tempted to believe that this is the radial component of velocity, but it is not. Radial component of acceleration, but it is not. Okay, this is not the radial component of acceleration. The radial component of acceleration will be obtained by using this acceleration vector dot r vector divided by mod of r vector. So acceleration vector was gj cap. I'm writing it again so that we can take the dot product. We don't have to go back 3 4 slides. R vector was ut I cap plus half gt square j cap. All right, and divided by magnitude of r. So let me take t out as the common quantity. So u square plus g square t square by 4 root of this. So the dot product becomes half g square, half g square t square. Am I right? Half g square t square divided by t root of u square plus g square t square by 4. Again, the one t gets cancelled, so we are again ending up with g square by 2 multiplied by t divided by root of some constant plus some other constant into t square, which is again an increasing function. So the radial component of velocity, it also increases with time. And if the radial component of, sorry, not velocity acceleration, if the radial component of acceleration increases with time and the overall acceleration is constant, so the transverse component of the acceleration is bound to decrease. It is bound to decrease. So that, there we have our answer. So A goes with P, B goes with P, C goes with P, and D goes with Q. So that would be the answer. All right. So A goes with P, B goes with, guys, it is not written correctly. It has to be P. You can check it out in the book itself. It is P. All right. B goes with P, C goes with P, and D goes with Q. It is misprinted here. You can check it out in the book itself. All right. Now we go to next question. So Question number 24, 25. It's a good question. It's an easy question actually. So the graph here, here you see the graph OA section is parabolic and AB section is straight. BC section is again parabolic. It looks more like a straight line, but it's a parabolic thing. All right. If you carefully witness it, if you carefully notice it, it is not a straight line. Okay. Now, so what happens? Like what is happening? So it's a tall tower. It's tower of some height which we don't know yet. We dropped one of the stones. The stone started falling, and the second stone is yet not dropped. So the acceleration of the first stone with respect to the second stone is g, and therefore you see the parabolic nature. So when does the parabolic nature turn into a straight line? It happens when you drop the second stone also. So the moment you drop the second stone, now both the stones are falling with an acceleration of g. But at the time when you release the second stone, the velocity of this stone was zero, while this stone was already going with some velocity. All right, and therefore the relative velocity will now persist. The relative acceleration has become zero, but the relative velocity will now persist, which basically means that the graph of s versus t will become a straight line. So this straight line, it tells us that the time when the second stone was dropped was 1 second, and then they were both falling freely with the acceleration of g. And at this moment, that is after 3 seconds, the first stone hits the ground. The first stone hits the ground, and as soon as the first stone hits the ground, the relative acceleration again becomes g, and therefore the graph turns parabolic again. So from this graph, what we can say is that the time of fall for the first stone was 3 seconds, and um, the time when the second stone was released was 1 second. So the height of the tower, we know that we released the first stone, it fell for 3 seconds, and then it hit the ground. So we can say that h should be equal to half g into 3 square, which will give us 45 meter. So the answer to this question would be 45 meter. That is G. The stone after releasing from the top of the tower takes 3 seconds to hit the ground. So that is the answer. So that is the logic that we use for this question. Now coming to the next question's answer of this would be D. That is correct. Now coming to the next question, it says that what is the when the first stone hits the ground, that is after 3 seconds, the second stone was moving with. Now, if the first stone has hit the ground and if the second stone was released 1 second after the first stone, so it has been 2 seconds since the second stone was released. So second stone has been falling for 2 seconds. So in 2 seconds, it will gather a velocity of 20 meter per second. That is g into t. Not only that, it will cover a distance of half gt square. So that is 20 meters. So it has covered 20 meters from the top. So the height from the base would be 25 meters because the overall height of the tower was 45 meters. So 20 meter per second is a height of 25 meters. So D option is the correct one as we can see here. So D option is correct. All right, students.